You see them every single day, right? Little silver dots crisscrossing the sky. But have you ever really truly stopped to think about how they do that? Well, today we are diving deep into the incredible science of aerospace propulsion. And it really all comes down to one thing: the raw power of a good push. I mean, just think about it. We're talking about a 300-ton metal tube, packed with people and luggage, just casually hanging out miles above the ground. It seems like it should be impossible. So what kind of force does it take to push something that heavy, that fast, through the air? That's the big question we're going to unpack today. Okay, so let's get a couple of key terms out of the way. First, you've got propulsion. It's just a fancy word for the action of pushing or driving something forward. And that forward force it creates, we call that thrust. Every single engine we're about to look at is, at its heart, a machine built for one purpose: to generate a mind-boggling amount of thrust. So, how do they do it? How do they generate all that thrust? Well, it all boils down to one simple, beautiful, fundamental law of physics, Newton's third law. You've heard it a million times. For every action, there's an equal and opposite reaction. That's it. To move forward, you have to push something backward. Every engine out there is just a clever way of doing exactly that. So, let's start with our first solution, which is maybe the most intuitive one. If the whole game is about pushing air backward, well, why not just build something that literally spins around and throws it backward? And just like that, you've invented the propeller. You know, the easiest way to think about a propeller is that it's just a wing, but turned on its side and spun around really fast. See, just like a wing, each blade is curved. As it slices through the air, that curve creates high pressure on one side and low pressure on the other. And that pressure difference is what literally pulls the airplane forward. It's a fantastic and elegant idea. Okay, but what's actually making the propeller spin? Well, for the most part, you've got two major options. You've got your classic piston engine, which, yep, works a whole lot like the engine in a car, burning fuel to create rotation. And then you have what's coming next: these super clean, super quiet electric motors that are powered by batteries. So how does that piston engine work? Well, inside every cylinder, there's this constant four-step dance going on. First, intake. It sucks in a mix of air and fuel. Then, compression. It squeezes that mixture down really tight. Third, power. A spark plug ignites it, creating a tiny, controlled explosion that shoves the piston down. And finally, exhaust. It pushes all the used-up gases out. That incredibly fast up and down motion gets turned into the smooth rotation that spins the whole propeller. Now, propellers are fantastic, but they do have limits. If you want to go really fast and really high, you need a totally new approach. You have to stop just spinning the air and start swallowing it. It's time to talk about the jet engine. And if you want to remember how literally every jet engine works, you just need these four kind of silly words: suck, squeeze, bang, blow. It's the unofficial motto for the entire world of jet propulsion. So let's break that down. Suck. The engine pulls in a massive amount of air through the front. Squeeze. Rows and rows of spinning blades compress that air, making it super dense and hot. Then comes the bang. That pressurized air gets mixed with jet fuel and is ignited in a continuous roaring fire. And finally, blow. All of that superheated, high-energy gas blasts out the back at incredible speed. That is your action, and the plane moving forward is the equal and opposite reaction. But of course, there are a few different flavors of jet engine. The original was the turbojet. It's pure suck, squeeze, bang, blow. Then there's the turboprop, which is kind of a hybrid. It's a jet engine whose main job is to spin a propeller. But the real superstar, the engine that totally changed modern travel, is the turbofan. And the key is that giant fan you see at the front. It actually pushes most of the air it sucks in around the hot engine core. And why does that matter? Because that bypass air, as it's called, is the secret sauce. It makes the engine way, way more fuel efficient and a whole lot quieter. This one brilliant idea is what made modern, affordable air travel a reality. The engine on that last flight you took, oh yeah, it was almost certainly a high bypass turbofan. So, piston engines, jet engines, these are amazing, incredible machines. But they all share one critical weakness, one fatal flaw. And to get around it, we need our third and final solution. We have to stop relying on the atmosphere around us and start bringing our own. And now we're in the world of rockets. So what is that big weakness? Well, all the engines we've seen so far are what you'd call air-breathing engines. They have to pull oxygen out of the atmosphere to burn their fuel. But you know what happens as you go higher and higher, right? The air gets thinner, so they start to lose power. And once you get to the vacuum of space, well, there's no air to breathe at all. They just stop. And right here, this is the big aha moment. This is the absolute key difference. Air-breathing engines, like a jet, are totally dependent on the atmosphere for oxygen. But a rocket? A rocket is completely self-contained. It carries its own fuel and it carries its own oxygen, usually in a liquid or solid form called an oxidizer. This is the rocket's superpower. This is what makes getting to space possible at all. A rocket engine couldn't care less if there's air around it. It has everything it needs to make fire packed right inside its own tanks, which means it can generate incredible thrust on the launch pad, way up in the thin atmosphere, and, crucially, in the total vacuum of space. So what does that power look like? Let's talk numbers. The first ingredient for thrust is exhaust velocity. A rocket shoots hot gas out its nozzle at unbelievable speeds. We're talking 3,000 meters per second. That is almost 7,000 miles an hour. But speed isn't everything. You also have to be pushing a lot of stuff out the back. That's the second ingredient, mass. This rocket here is blasting out 20 kilograms, about 44 pounds, of superheated gas every single second. And when you multiply that insane velocity by that constant flow of mass, what do you get? You get 60,000 newtons of pure, relentless force pushing that rocket skyward. That's the incredible power of rocket propulsion. Okay, let's pull all this together. We've seen 3 completely different ways to solve the problem of generating thrust. And maybe the most important thing to understand is that each one is a very specific tool for a very specific job. This little cheat sheet says it all, really. Electric is great for drones and small planes, but batteries are heavy and don't last long. Piston engines are perfect for small private aircraft, but they can't fly high. The turbofan is the king of efficient travel inside our atmosphere. And the rocket, well, the rocket is the only tool we have that can leave our atmosphere behind completely. And that's really the big takeaway here. There is no such thing as the best engine. You wouldn't put a giant rocket on a tiny training plane, and you sure can't get to Mars with an electric motor. It is always, always about matching the right piece of amazing engineering to the specific mission you're trying to fly. You know, when you look back, from the first piston engines to the most advanced rockets, you could argue that the last 100 years of progress were all about getting better and better at burning things. Which leaves us with a pretty cool question to think about. What comes next? What new ideas, what new physics will define the next century of pushing ourselves even faster and farther than ever before?